Good evening and welcome to another episode of Adventures in Haskell. Tonight we are going to go that final step and we are going to add proper native compilation to our BF implementation. So the way that we're going to do this is we're going to use a compilation suite called LLVM, which is the low-level virtual machine, and basically there is a nice neat Haskell binding, which I will put the link in the description for, to the LLVM package, and using that we're going to generate LLVM bitcode, which can then be turned into native code. Depending on how much time we have, we may or may not go as far as generating the full executable, but we'll definitely go as far as generating an LLVM bitcode file that can then be compiled to run natively. So, what we're going to do first is we're going to add a new action to our command line parser so that we can, instead of parsing or interpreting, we can get the bitcode out. And we need to add an argument that enables bitcode, so let's do that. C, why not? Bitcode. Bitcode parses the input and outputs a bitcode file. Now before we just said if action is parse only, print else eval. It makes sense at this point to change that into a case action of parse only, interpret, and bitcode goes to write bitcode file, giving it the instructions, and we need to give it a file name that it's going to write to. We have a file name in fname tick, and the reason that this was up here, the system.filepath.posix, is because there is a really handy replace extension that's going to allow us to replace the file extension of .bf with .bc for a bitcode file. So replace extension fname tick with .bc. Now we need to import system.filepath. In order to do this, I think I meant that. So all we need to do now is write our bitcode file. So let's put a nice simple compiler section in, and off we go. Write bitcode is going to be a list of instruction to file path to an IO action. Right, now actually writing the compiler is going to take more than a few moments. I have written one before, so I'm mostly going to be cargo culting that across. Rather than you lot watching that, what I'm going to do is pause here and give you a smiley rock, and once I've brought everything across, I'm going to walk through the compiler with you. So, excuse me. And welcome back. The first thing that I've done is put a body on the write bitcode file method using new module, which is an LLVM binding function which generates a new LLVM module, which is like the compilation unit with LLVM. Then defining that using a function that I've written called compile body that takes an instruction stream and produces a function body which is going to be called main, so that we can actually compile and execute this. We then optimize it because frankly my compiler that converts BF bytecodes into LLVM bitcode is naive. And finally write that bitcode out to a file. All of those functions you can find defined in the LLVM core module, which has all sorts of things in it like new module and define module and so on. Now the compile body function is a little long, as you can see, but we'll go through it bit by bit. So the first thing to know is that it takes a list of BF instructions and it produces a code gen module which is of a function which takes no arguments and returns a word 32 in IO. And we have to say IO because ultimately we're generating something that runs native code and could do anything, so we have to be clear about this. Then we acquire 3 functions, or rather we get effectively 3 link inputs. So we're saying there is an external getChar function, which is a function that takes no arguments and returns an IO word 8. There is putC, which is a putChar function that takes a word 8 and gives you back an IO empty. And there's B0, which takes a pointer to a word 8, a word 32, and returns you an IO empty. So that's the getChar, putChar, and B0 functions. Then we're going to create a named function. This is actually what's going to get put into the output, and we're going to call it main, and we are going to create a pointer, head P. Now, it may look strange to just go alloc done, but basically by virtue of the type definitions that we have as we go through this, it can work out that head P is a pointer to a word 16, and the reason for that is that we're saying that we have a tape of 65,536 entries and that it will wrap around, and this is quite common for BF implementations. It's not as pure, shall we say, as the Haskell implementation, but it'll do for us. Then we have tape, which is an array alloc of 65,536, which we have to say is a word 32, and that whole array allocation is a function call which is going to return to us a value which is a pointer to word 8s. And again, all that does is it uses the fact that type annotation can help the LLVM code to work out that what we're asking for, therefore, is an array of 65,536 word 8s, because obviously each entry in our tape is a word 8. Then we store the value of 0 into head P, so we initialize our head to point at entry 0 in the tape, and we call B0 on the tape parsing 65,536. Again, the use of value of here and the use of value 0 here look weird, but it's just necessary in order to get all of the appropriate type annotation information in there so that the LLVM binding can work out exactly what we mean without us having to tell it explicitly. It looks a bit nasty here, but when you have more complex code it works very well. Then what I've done is I've defined a function internally called compile instruction that takes a BF instruction and returns a code gen function R0 terminate. Again, looks a bit weird, but basically terminate in this instance is the identity monad, because we don't want to do anything clever inside. We're not doing any IO or anything underneath, although we could. So code gen function is basically saying, and here's a chunk of code. Compile instruction go back, loads the head out of the head pointer, subtracts 1 from it, and stores it back. Go forward, does the same with adding 1. Now increment and decrement are where it gets interesting. We still load the head value out. We then have to 0 extend it, and the reason that we 0 extend it is because we need a word 32 to index our array. A bit annoying, but hey, it's the way it goes. Then getElementPutter is an LLVM function which takes a pointer to an array, so tape, and then it takes a number of ways to look through the thing that you're indexing. So all we're saying at this point is that we are indexing into tape with head as a word 32, which is necessary in order to make getElementPutter work. And then this empty here signifies the end of the chain of things that we're trying to look through. In theory, if you had a struct and that struct contains another struct and that contained another struct, then you could sort of jump through and look through arrays and so on within those structs, all in a single getElementPutter. It's really important to note, though, that getElementPutter does no memory access. It's purely the calculation of an offset within a structure. So then we load the value with using that value pointer, we add 1 to it, and we store it back. Decrement exactly the same, only with a subtract. Input, we get our head, we get our element pointer, we call getChar, and we store that in. Easy peasy. Output, again, we get our pointer, we load the value off the tape, we call putChar, and we return empty to say, well, there's nothing more for us to do here. If we don't have that return empty there, then this gets angry, and the reason it gets angry is an enormous error to do with IOA and IO empty and so on. And basically what it boils down to is everything else within this the compile instruction stuff ends up returning nothing, where calling putc there actually theoretically might return something, so call gets a bit angry, so we'll just stick that return in and ignore the result of call. Finally, looping. Looping is a bit weird, and the reason that looping is a bit weird is because there is these basic blocks that go on, and we need to be able to handle jumping around because there's code from before the loop, there's code from code at the beginning of the loop which says should we do the loop at all, there's the loop, and then there's code at the end to jump back to the check. Because this is a while loop, that's effectively how we have to represent it when we compile it. So the first thing that happens is in the code before the loop, we branch to the top of the loop. Then our top of the loop does our test. So we load in the head pointer, we 0 extend it, we acquire the value from the tape, and we compare it to 0. We then do a conditional branch, and the conditional branch takes the test value and what to do if the test succeeded and what to do if the test failed. Because we're using CMP-NE here, then success means non-zero, so we go ahead and do body, and failure means 0, at which point we exit. So then we define a body block, which is compile the instructions within our loop. Then we branch back to the loop point, which again jumps back up to here and does the test again. Then we just say define basic block exit, and then any instructions that get compiled after this loop are effectively within this basic block. Looks a bit weird, but it does work. Finally, we define a compile instructions function, which just does a map-m of compile instruction. The whole main, as it were, is then compiled as compile instructions with the incoming instruction stream, and then return 0, because main needs to return 0 in order to be a good and friendly part of Unix. This is all in the Git, and it will be pushed, and the URL will be in the description, so don't worry too much. Now, one of the problems that we have using LLVM is that we can't now use runghc. It's unable to link everything together properly. It's annoying and unfortunate, but it's the way it goes. So we have to now compile our BF interpreter using ghc-make. Once that's done, however, we now have our -c or --bitcode, and if we try that on example hello, oops, examples hello, there we go, then you can see that we have a hello.bc. Now LLVM supplies a really convenient tool called LLVM LD, which is a linker. Bitcode files are effectively compiled objects. It's just that you can't link them with normal LD, you'd have to use LLVM LD. If you wanted to, then you could use LLC to compile a bitcode to a .s, and then you could use normal as or GCC and so on. But we're going to use LLVM LD, and we're going to output to hello from examples hello.bc. We have an executable, and if we run it, we get hello world. So this is working for us. We can take our input BF file, we can generate an LLVM bitcode file from it, we can then link that into an executable, and we can run it. In theory, rather than writing the bitcode out to a file, we could just run the code internally inside our BF, but at that point we may as well interpret it, because unless it's a really huge program, it'll be just as fast to interpret it as it would have been to byte compile it. And if it's really huge, then byte compiling it and then having the executable afterwards is of more use. Next time we'll look into being able to run LLVM LD ourselves from the Haskell code, so that you don't have to run it yourself, and then we don't have to keep the bitcode file around. Bye for now.